In this session, JF Bastian is going to talk to us about the portable native client.
Right, thank you. So my goal today is to kind of present what portable native client is. Most of you probably know something about it. So I'll try to demo what we're to showcase what we're trying to build and why we want to do something, right? And the goal for this is that portable native client started, a few years ago, and it wasn't very clear what we were trying to do. I don't think it was clear to anyone at Google either. And so what I'd like to do is to kind of showcase where we are now, what we launched a few months ago, and why we do things a certain way, right? And then that kind of helps give the context for what we want to do with LLVM, how we want to contribute to LLVM, right? We definitely want to send a bunch of code to the LLVM community, but sometimes we send code and people are like, what are you doing? That's really weird, right? And I think kind of giving the background of what we're trying to do and what it enables is really helpful. And then it helps explain what our strengths are, right? What we can bring to the community and why we do things a bit differently and maybe why the community should care about it. So that's what I'm going to try to do today. And if you have questions, just raise your hands. So basically, you probably know native client, right? pnacl. That launched something like in 2008. It was based on GCC. And basically what it did is it tried taking completely unsecure code we don't trust at all, and it tried making it provably secure. Now that sounds a bit ludicrous. To do that, it was using something called software fault isolation, right? So there's a paper, there's a link in the slides that you can go to, but basically what we did is we isolate all the memory accesses as well as all the branches inside the code base. And so it allows us to look at the code base bundle per bundle and prove that memory accesses don't go out of the sandbox that we've predetermined, as well as branches don't go out into locations we don't like. And for example, you can't go in the middle of an x86 instruction and execute from there, right? So if you had an immediate that happens to look like a very malicious syscall or something like that, you can't just jump in the middle of the immediate and execute from there. So you'll have to trust me that it's nice, it's very small, it's detailed in the paper. But basically, that was the idea. So what we did is we modified GCC, and so that allowed you to compile C, C++ code, or whatever else you want, right? So an interpreter like Python or Lua or something like that, and execute it within a small, secure sandbox. Initially, the launch supported x86-32 and x86-64, and later on, we added ARM support as well as MIPS support. Now, native client itself is kind of like a small operating system. So it has all these shims that you can call out to that then call to kind of a trusted code base that do all the operations an operating system would do. Right? So what's nice with native client is you can target a bunch of different architectures, and you don't really need to care what the operating system is underneath. Right? So it supports Windows, Linux, Mac, Chrome OS. It just kind of works. And so that's great. We have security out of that. We have simplicity in the way the sandbox is implemented, and the way the trusted code base is very small, right? And you can just run your code and it works. And we also have speed, right? So obviously, the sandboxing has some cost, and it's about 10 to 20% in most cases. In some cases, there are kind of edge cases you can build where it'll be more. But in most cases, it's 10 to 20% cost. And so pnacl was kind of a nice base to work from. Now, the problem with pnacl is that, well, it's architecture specific. Sure, you can target x86, you can target ARM, you can target MIPS, but you don't really want to ship that on the web. Right? Initially, that was kind of the hope that people would be like, oh, that's awesome, just ship x86 on the web. That was kind of a dumb idea in retrospect. So what portable native client tries to do is it tries to take what native client gave us and actually make it portable. That's the main thing that it does. Okay? And I'll explain what the architecture choices we made for portable native client then enable. Right? So think of native client kind of as an implementation detail of portable native client. Right now, portable native client is completely built on top of pnacl, but that's not necessarily the case for the future. So you probably think that you know Portable Native Client. We've sent things upstream, and we've had very lively discussions that were very entertaining and provided lots of popcorn to the community. That was great. What I want to do is really explain what we're doing and kind of say why we think it's the right thing, and kind of really explain that we're not trying to ship LLVM bitcode, and we don't want to force the community to make bitcode stable, right? Like, we'll deal with the stability of the bitcode. So the first thing that Portable Native Client tries to do is to be a part of the web platform that Chrome ships, right? So we launched late last year, and basically on any Chrome browser you can go on a web page and load up what we call the portable executable, and on your machine it'll translate the code from this portable executable to platform-specific code. Now again, as an implementation detail, that translation process happens to run inside a native client sandbox, right? And further, there's also an operating system sandbox around it, right? So we really want to keep our users safe, but we want to give you, the developers, the speed that you want to have. Now, basically, pnacl kind of fixes the main objection that didn't get pnacl onto the web itself, right? That it's not portable. pnacl is portable. Again, it supports x86, 3264, ARM, and MIPS, and we hope to be able to support any other architectures that come along. And when I said, okay, we optimize the code on the device, we translate from portable executable to native code, you're going to say, well, okay, so you're using LLVM, and it's a ginormous code base, right? So how do you even know that the code you're generating is safe? Well, we don't. We don't trust LLVM at all, right? So basically, when we translate the code from portable to non-portable executable on your machine, we run LLVM. LLVM runs inside a pnacl sandbox itself, right? So we don't trust it at all. You could exploit LLVM all you want. You'd have to leave the two sandboxes to do anything malicious. Furthermore, the code that LLVM generates is also completely untrusted. And so we also validate that code to make sure that it actually follows the rules of the sandbox, and that therefore it's also safe, right? So basically, the security review we did before launching Portable Native Client was, you use the pnacl sandbox? Yes? All right, you can ship. That was the entire security review was basically that, right? We argued a bit about some things, but that was about it. Now, the other thing that we do is we also give you bindings to some of what the web does, right? So the web has HTML and JavaScript, and it has a bunch of other things. And so you can access all of those from Portable Native Client, right? So our goal is that you can just run C or C++ code or whatever else you built on top. And if you want, you can also talk to the rest of the web, right? So you can do kind of a black box thing that takes over the whole screen and that displays, you know, a game or something like that. But you can also do kind of a thinner kind of integration where Portable Native Client does one thing and the rest of the web platform does the rest, right? So your UI could be built with JavaScript, and the rest of your code base could be run in Portable Native Client. And they're, you know, you can just mix and match however you want. All right. So as I said, you can just do compute offload. And really, we want you to be able to use the full power of your CPU from within Portable Native Client. So we really don't want to be squandering CPU resources left and right and just throwing that away. And at the same time, we want to give you access to everything that you would expect from a regular platform, right? So I've listed a few of the features that we support. Not all of them are currently fully supported right now. We're still working, for example, on supporting really fast SIMD and crypto, right? Because it has to be portable, and that's not trivial with SIMD, which inherently isn't portable. Same thing with dynamic linking. We don't want to just say, oh, you get the glibc dynamic linking interfaces. That doesn't really make sense from a web perspective, right? Because you're going to link something dynamically. It's not just going to load it from the hard drive. It's going to load it from a server far, far away. And there are a lot of interesting things that we can do with dynamic linking inherent to the web platform. But besides that, what we want to give you as a developer are things like POSIX, right? You expect to just be able to do all those calls, and they just work, right? And in some cases, what we do is we provide kind of a shim library that you ship with your code that just emulates all of POSIX. And you're going to say, ah, well, What about file systems? Yes, we also support file systems. Now, obviously, the web platform itself doesn't usually have file systems. And so what we do is we go through the usual access controls that the web platform offers. So if you start writing to the user's disk, you're going to have temporary storage, and at sometimes you're going to run out, right? So you can always ask the user for quota, right? So most of your code can just be the same. Just at the start of main, you can mount the HTML5 file system. It'll ask the user for quota, and if the user gives you the quota, you're good to go, right? Otherwise, you get just some temporary storage that will be reclaimed from you at some point. And you can do the same thing with, for example, instead of mounting the HTML5 file system, you could decide to start talking to Google Drive or to whatever other storage like Dropbox or something like that. And if you start doing that, well, it'll look like a normal POSIX file system, but you'll have to do all the remote calls, right? And the shim layer can be the one doing that for you in the background. Now, also we support OpenGLES, same support that Chrome has, and we support threads and atomics, right? So you can just start up a bunch of threads if you want. You can use C++11 atomics as much as you want. Everything should just work. So really, the goal of Portable Native Client is to give you a platform that gives you full access to your system's capabilities. And basically, it allows you to build a lot of interesting applications. So we've had a few demos that have, for example, a DOS emulator or an Amiga emulator, which surprisingly got a lot of attention because people really liked Amiga. Then we have nice little ports left and right. Like we have just Vim running inside the browser. We have Emacs running inside the browser. And what we're trying to do now is we have all the technical details down to be able to just have bash and fork anything you want, right? So just from your browser, you should be able to just run bash and then start Vim, start editing something, run LLVM, generate a binary, run that binary. You should just be able to do that. We just haven't finished doing it yet. But a lot of the pieces are in place, right? So little Chromebooks like this thing here should just be able to run everything within the browser. That's one of our goals, and everything's in place. We just haven't finished it. But in the next few months, we think we'll have kind of a nice platform that just runs. And again, because of the remote file systems you can use, you could just from your browser edit things remotely, and then never really have to store anything locally. All that nice stuff. Another thing that we're doing is we're slowly porting random applications left and right. And when I say porting, it's really just like, hey, here's a few special things you need to do to make your application run, and that's it. So for example, some folks at work recently ported, a few months ago, ported Google Earth to native client, to Portable Native Client. And it was kind of disappointing because Google Earth is this ginormous application that pulls in a bunch of code from Google internal things, and it just kind of worked. So we got pretty much zero feedback from them. And I have a demo that I can show folks afterwards if you want to come and play with Google Earth in the browser. It's not really anything special because it's just Google Earth. It just happens to work in the browser. So there's a lot of interesting things that we do like that. And for example, we also do some photo manipulation within the browser. We do the hot word recognition. So you can enable in the browser just the kind of Google Now type of thing where it does voice recognition. So you say, OK, Google, and it starts listening to what you say, and then it types it in for you. So that type of stuff just kind of works. And so as we launched at the end of last year, we've been kind of trying to figure out how do people use Portable Native Client. The problem is that it runs on the web. We have no clue what people are doing. We know what people internal to Google are doing. We have no clue what people outside of Google are doing. So we're trying to have kind of educated guesses as to how much our platform is being used and what we can improve, where does it crash, things like that. And right now, we're pretty sure after a year, there will have been a few billion uses of Portable Native Client. We're not quite sure how many. But the order of magnitude is in the billions right now that we expect at the end of the year. So that's pretty sweet for something we just launched recently. And then I talk about the web a lot. Most people here don't really care about the web. It's this thing you use, and that's about it. Right? We don't really want to develop for the web that much. So Portable native client also, so okay, it works in a browser, but it also, for example, is useful for a data center, right? So you run a bunch of untrusted code sometimes in a data center, more and more with cloud things, and you don't really trust that code, right? So you'd like your web server to be small and nimble and just kind of be able to run code, right? So there's a company called ZeroVM that does that using native client and looking at portable native client where basically you just kind of run things in a sandbox. There's the same thing with, say, the Chrome browser has a bunch of code that it pulls in that it doesn't trust at all, right? Chrome gets exploited not that frequently, but from time to time. It's often some really stupid bug with a code base that wasn't really built for security, and it's really annoying, right? It's just some wild pointer that dereference or something like that. And one of the things we're experimenting with is taking different parts of Chrome, like say some video decoding or some image processing or something like that, and running it within a pnacl sandbox, right? So the idea would be that you have all these different blocks that you kind of put together, and they themselves are in a sandbox. So I'm not talking about the web anymore, right? I'm talking about an application having different sandboxes that you don't trust. Or say you have this great programming language that has all these great type systems, and you can prove that the application is correct, assuming your compile is correct. That's really cool, right? There's all these languages that do stuff like that, but then the reality kind of sinks in at some point that, well, you can't rewrite all of the world's applications with your language, right? And so what's really interesting is well, you could pull in different parts of say, FFmpeg or something like that. Just pull it into your application that has all the nice type systems, and then just do the calls to FFmpeg inside a sandbox, right? So FFmpeg could be sandboxed, the rest could not be sandboxed. And then you get the advantages of security and the speed and simplicity, because you pull that in and it just works, right? So that's what we're trying to do outside of the web platform. And at the same time, there's all these other devices that are coming online. So for example, you can buy today a Samsung TV that has portable native client inside of it. So there's a bunch of really interesting devices that could just be running portable native client, and everyone kind of wants an app store. It'd be nice if they weren't all insecure, right? So that's kind of what's nice about portable native client. And at the same time, it kind of enables something nice where Samsung, say right now, uses ARM chips. If Intel really, really tries to kick ass with their chips, well, Samsung can switch to Intel and it just kind of works, right? So it gives you this flexibility to run on different hardware platforms, right? So that's kind of nice. All right, so I've talked about a platform. What does it do? What we're trying to build. Why should you care, right? Basically, well, we have a really nice reach. We're really committed to portable native client. We won't just remove it from Chrome tomorrow. So what's nice there is we have all these use cases, right? And a bunch of users. And it's a bit different from what LLVM has traditionally cared about, right? So what we'd like to do as community members of LLVM is contribute in those kind of novel areas, right? And I'm not saying doing weird-ass things with LLVM and pushing them in, right? I'm saying things like, hey, we care about compilation speed. We'd like to improve that, right? There was that question yesterday at one of the presentations, like, does anyone actually care about compile speed? Yeah, we do. And we've tried to improve it a bit. We haven't done as much as we could yet. So that's the type of thing that we'd like to bring to the community. And at the same time, what's great is we have a pretty big reach, right? So as I've said, we expect to have a few billion uses per year this year. That's a lot of times that LLVM has run in people's web browsers, right? Like, we've run LLVM a lot. And there's a lot of interesting things we can do with that, right? So we could instrument LLVM and make it faster just through that, right? We have all these users that actually care about it. And I'll detail later other really interesting things that we can do with the platform because of that. But first, I'll try to explain what do we actually do with LLVM. We actually use it in two completely different places. And in a way, they're completely separate. We could do away with one, do away with the other. Now, what's interesting with that is, OK, so we could do away with, say, on the browser side, we could not use LLVM if we wanted to, right? as a proof of concept, we could write our own kind of backend. We're actually doing that right now. We're trying to see, all right, well, how fast could it really be within the browser? What could we throw away and really have this kind of lean and mean compiler that compiles exactly the portable executable to the native code, and then that's it, right? And that's kind of interesting for us. But stepping back a bit, we use LLVM on the left side for the developer, right? So it's just like any traditional use of LLVM, except what we do is we use LTO, right? So we take everything, even your C library, and we compile it into one big module, so an LLVM module. Our platform just assumes the little endian 32-bit, and that's about it. We run opt on it, and we run pretty much all the optimizations that you would run within a regular compile, except none of the target-specific ones, right? So in some cases, we'll run kind of an architecture-independent target and optimize with that, but the rest of the optimizations are, everything you would usually run with LLVM. Put in the C library, and all it does is syscalls to the kind of native client shims. But that's about what we do, and then we generate what we call a portable executable that I'll explain a bit later. And then on the other side, the browser does the translation. All right, so portable executables. Basically, what we ship on the web is an SSA representation of code. It has functions. It has a ginormous global array. It has some types. It doesn't really have any relocation to speak of. And it pretty much only has arithmetic operations. So it kind of sounds like LLVM bitcode. It's strangely inspired by LLVM bitcode, but it's somewhat different. So one great thing is because we do LTO, we can throw away a bunch of things. Right? Relocations don't really matter anymore. The types, well, we all lower all of them, right? So all the user types are kind of set in stone in the portable executable. All the offsets are set in stone, things like that. And basically, we support all the C integer types that you'd expect, right? So you have bool, int 8, 16, 32, 64, and you have floating point 32 and 64. That's it, right? We don't support all of the weird integer types. We kind of just legalize all of them. And then that allows us to remove a lot of the complexity that you would usually have within bitcode. And I'm not saying it's bad complexity, right? That complexity is actually useful for a lot of optimizations. Now, it happens that we ran most of the optimizations anyways. So we can do away with those types and not really lose any performance. One of the things we do is we kind of track compiling an application with these ABI simplification passes and compiling it without. We benchmark each against each other, and it pretty much comes out even, right? So because we've run all the optimizations before, the fact that we simplify the ABI doesn't really lose us anything. And sometimes it does, but most of the time it doesn't. And as I said, instead of having all these different globals with a bunch of different types, it's just one ginormous global array that's a big byte sequence. So you don't care about a lot of what LLVM would usually care about. You don't have const exprs within the ABI representation. Another thing we do is, so we support threads. Threads usually have this TLS layout. It's usually pretty complicated. We just kind of pre-lay out TLS. Another thing is we only export the underscore start symbol, right? So the only thing that is actually exported is start. And then there's this initial init and finalization list of functions to call. So all the constructors and things like that go into that initialization and finalization array, right? So everything is pretty simple on top of the usual LLVM platform. A few things that we want to continue improving is undefined behavior. So a lot of the undefined behavior is kind of set in stone at the point of the portable executable, right? So a lot of the times what happens with, say, an out-of-range enum or something like that is already predefined when you reach the point of a portable executable. But there are a few things like, okay, if you start having data races, it's kind of hard to really nail down that undefined behavior, right? There are other simple things like, okay, you divide by 0. On x86, it'll do one thing. On ARM, it'll do a completely different thing, right? Integer divided by 0 on ARM just returns 0. So one of the things we guarantee is that when you divide by 0, it'll actually abort. So, kind of simple things like that. And then, shift by larger than width or things like that can be nailed down pretty easily, right? The problem is if you add checks everywhere very eagerly, you're throwing away a lot of performance, right? But we do want our platform to perform exactly the same on all the architectures, right? So slowly we're improving how we define undefined behavior without actually giving away too much performance. Any questions? So one thing that I haven't really mentioned is debugging. So Dwarf happens to be Turing complete. We don't necessarily want to ship debug information inside the portable executable, especially since it changes a lot. And so usually when you want to debug an executable, you can attach to it. And if you have debug info, you'll see something useful. If you don't, you won't see anything useful. And that's kind of the same thing with portable and native client. When you create a portable executable, we throw away all the debug information. We rename everything to just 1, 2, 3, 4, 5 instead of actually having function names. And that's kind of useless for debugging, right? So you could attach to the native executable that was generated from your portable executable. It won't really do you much use. You could step through it with GDB, do all the usual stuff, but it's not really nice to debug. So it's also possible, instead of doing that, to have Chrome load a non-stabilized portable executable that has all the debug info in it, right? So debuggability is also something that we actually care about, and it should just kind of work, right? So you just have to say, don't create a portable executable, and everything should just be debuggable very nicely. All right. So we kind of care about a lot of interesting things on the code generation side. So basically, we really want code generation to be fast. And when I say fast, I mean you download the portable executable, and once it's done downloading, it's also done compiling. That's our target. That's really, really fast compared to what LLVM traditionally does. Right now, measuring how much time it takes to compile a portable executable to a native executable, reading the bitcode and generating IR is all you're allowed to do before you're done downloading, right? Like we spend all of the time it takes to download reading IR and generating it. We don't have any time to do any lowering, any optimizations, nothing, right? So right now the situation is not as good as it could be. So one of the things we really, really want to do is make the very back end of LLVM much faster, right? So as I mentioned earlier, we're experimenting with a separate code generator that uses different pieces of LLVM, and we hope that that'll inform kind of some of the design space for making the back end faster, right? So we want to have something that's faster than FastICell, but that happens to generate code that's better than selection DAC, or at least as good, right? And one of the advantages we have that most people working on LLVM don't care about is we've run all the optimizations before, right? So you probably won't see many commits from us optimizing all the big optimizations. What you'll see from us is we'll try to make the rest of the backend faster, right? So for example, a year ago, FastICell wasn't even enabled on ARM, right? Which is kind of silly. It's just that Apple created FastICell, made it work on their platform, and then gave the source to the community. That's great. Someone needed to do the work to make FastICell work on ARM, and we did that. And so it's kind of something useful for us. And then one thing we care about is that the size of the translator itself, right? So the executable that we ship to every Chrome device out there is actually kind of big, right? And LLVM is this big monolithic thing, and it's kind of hard to cut out pieces that we don't care about. For example, the translator that gets sent to ARM devices that run Chrome has all of the ARM backends for ARM v5, ARM v6, ARM v7, and all the subsets of that. We don't care about any of those except ARM v7, basically. And it's kind of hard to cut that away without making really ugly modifications to LLVM that make it hard to kind of take the upstream patches, right? So we want to be on LLVM 3.4 and the intermediate versions to 3.5. And if we start modifying left and right LLVM, that's just a bad idea. It doesn't really work out very well. So one of the things we want to improve is the size of the LLVM binary and how good it is at removing code you don't use, right? So what we want to do is be able to have LLVM compile itself and really see, all right, well, here's what I'm actually using, and be able to throw all of the useless stuff away. Useless for us, right? It's not useless for most people. And so basically, the changes we want to do would improve the situation for pretty much anyone who uses C++, right? We're not trying to just hack something out and make it work for us. We're trying to add passes to LLVM that allow it to compile itself more intelligently and remove useless code for that executable. Same thing with function commenting or something like that. A bunch of people have written code to do function commenting, and it's not enabled in LLVM right now. And we'd like to improve the situation there. Another thing we care about is the amount of memory that the LLVM uses while it compiles, right? So a lot of times we'll run on pretty constrained devices, and if LLVM starts using all that memory to compile, well, that's not very nice, right? The application may be very small, and LLVM starts allocating a bunch of memory. That's not the greatest thing ever. So we're trying to improve that too. And those are things that we're trying to do with LLVM, trying to improve the platform. There's a bunch of interesting things that we can do with the pnacl platform also that we think that we can add to pnacl and really have the platform become better. So for example, all right, we send a portable executable to your laptop. Your laptop, for example, here is an ARM Chromebook. Right? It has an A15 chip in it. Now, ARM added integer divide to A15 chips, right? So you can just do an integer divide. That's really great. It happens that most of the time that you generate code, you never generate integer divides for ARM because you have no clue whether the platform supports it or not. Now, with Portable Native Client, we know exactly what platform you're on, right? So we can generate integer divides. Same thing on Intel. You have AVX. Hey, we could generate vector code that uses AVX. That's great. Right, so there's a lot of interesting things that we can do when we know exactly the ISA that you're running on. Right? So we can actually tune the code to run on exactly that platform. Now, one thing we can do also is we can actually tune the sandboxing to the platform. Right? Native Client has this kind of generic sandbox, and the sandbox is, in a way, an ABI. You can't really change the sandboxing ABI, right? Because an x86 native client executable has to run on all x86 platforms that we want to support. You can't change the ABI of that. You can't add new features. It happens that Intel is adding interesting features like bounce checking to their ISA, and we couldn't just change the sandboxing model without breaking native client on other platforms. Now with portable native client, we know exactly the sandbox that we'll run in, we know the ISA it's running in, and we control the compiler. So if we want to create a sandbox that uses the new features of the ISA, we can. Right? And this isn't just a security thing. It's not just about, hey, let's use all the features for security's purpose. It's also, that allows us to generate faster code, right? So reduce the cost of sandboxing by really taking advantage of the platform. And what it also allows us to do is to really tune the sandbox to what your code is doing. Right? So for example, certain types of code will be very branchy and will prefer a certain type of sandbox, whereas certain types of code will be very memory bound and will prefer another type of sandbox that doesn't really put such a big burden on memory accesses. Right? Something else we can do is we know exactly the OS you're running on. Right? And in some cases, we actually control the operating system also. Right? So for Chrome OS or Android, we control the operating system. We can do a lot of interesting things in partnership with the operating system. And because we control the compile step, well, we can generate code that really takes advantage of the operating system. And finally, we could generate your code with, this part of the code runs in a certain type of sandbox, this other part of the code runs in a different type of sandbox, and just have kind of a transfer mechanism between one sandbox type and the other. Right, so that's the type of thing we're working with. And because we kind of shed our ABI dependency on the native client sandbox, we can do all that work, just do the experimentation and modify LLVM all we want and have it generate different types of code and play with that. So that's something that's actually really interesting. Something else we want to do is kind of take advantage of the profile-guided optimizations that are being added to LLVM. So we can run your code once and then regenerate it in the background using the profile-guided optimization information we gather. One of the things we're also playing with is maybe doing that at runtime, right? So just do runtime code generation. It'll still follow the sandbox. It'll still be validated before being mapped as executable, but we can kind of progressively generate code that'll run faster. It sounds a bit crazy. It kind of is, but there's a lot of interesting stuff we can do there. Something else we can do is we can totally hide the code from the user, right? So to make it hard to build an exploit, we can just make the code completely hidden, really separate the data that you have from the code, right? There's a lot of interesting things we can do there while still following what the C++ standard says should happen. And lastly, there's all these really interesting things that are coming into to LLVM that we want to help with. So Tom Roeder recently sent the start of a set of patches that adds control flow integrity to LLVM. Basically what that says is all of the branches go to known function entries or internal to the function locations that are known to be safe. Now that sounds a lot like what native client does. It actually is, but his control flow integrity relies on LTO and on the semantics of the language to make sure that you only enter functions at places that make sense. So it kind of builds on top of the native client sandbox very well, right? So it allows you to really ensure that the code does what you expect it to do, right? So the traditional native client sandbox basically ensures users' safety. It ensures that you don't escape the sandbox. CFI goes further and makes sure that the code is kind of more protected from malicious inputs. For example, if we built LLVM with CFI, that would give us more certainty that the code LLVM generates, even though we validate that it's correct, that the code it generates isn't under attacker control, right? It only generates code in a way that was intended by the LLVM compiler. And that's very powerful. At the same time, the UCI folks are adding randomization to LLVM. And so what's really great with randomization is that every device that runs an executable can have a completely different executable. And that makes it really, really hard to exploit, right? Because every different device has something different. And basically, that's a great way to provide defense in depth while also improving the rest of the sandbox. So we're really excited about that, and we really want to contribute to those type of improvements. So in general, that's what LLVM, what pnacl does, how it tries to use LLVM, and how we want to contribute to the platform. So with that, if you have any questions.
Thanks, Jeff.
I'm a bit confused with what you do on developer side and on user side. You mentioned several times that you run LLVM inside user machine.
Yeah.
And then you said that you do whole optimizations plus LTO and generate something, and this goes to user machine. And then you said that your binary code is not LLVM IR.
Mm-hmm.
So what exactly you run on user machine, and does this thing, how much it is based on LLVM, and does it consume LLVM IR binary format, or what?
Yeah, so we're actually trying to write a more formal spec of what that intermediate representation is. We have kind of a high-level description of it in our documentation, but it's not that useful. So basically, here's an example. LLVM has getElementPointer, right, which is this really powerful thing that's really useful in a lot of cases that allows you to index into something, basically. Now, what we do with the getElementPointer is we effectively lower it to a bunch of adds and multiplies. And so what you do is on the developer side, you use the geps as much as you want. And then in the PEXI, you lower it to adds and multiplies. And then on the user side, all you see are adds and multiplies, right? So what we've done is we've kind of done away with the concept of a gep. If we wanted to, we could reconstruct the get. Now, obviously not perfectly, right? But on the user side, we could reconstruct the geps if it makes sense, just recognize the pattern. Or we can just treat it as an add and a multiply, right? So I don't know if that's an example that kind of helps you see what we're doing in the PEXI and on the user side. So effectively, today what we do is we reconstruct LLVM IR, but using only very few features of the IR that LLVM exposes. right? Now, as I said, if you were to build a completely independent compiler, it could still be able to read this SSA form and construct, very basic IR that doesn't have all the same concepts that LLVM has, right? So it would have one module, one function, CFG, a bunch of instructions, but the instructions would be only on the very basic types that we expose, and only use the very basic instructions that we expose, like add, multiply, divide, things like that, right? So I don't know if that kind of helps answer your question of what are we doing on the user side. We are running LLVM, but a very small subset of what LLVM traditionally has. And if we wanted to, we could reconstruct a bunch of the information if that were actually useful. Now, because we measure performance with and without that ABI simplification, we'll know if we're throwing away stuff that we shouldn't, right? Or if we should reconstruct things that would help us gain more performance. And right now, that hasn't really shown up, right? So does that answer your question?
Well, just to make sure I understood it. So the first thing you do is translate from pure binary format to LLVM IR, and then run LLVM on the standard LLVM IR.
Yes. Yes. But basically, if you looked at the hot functions in the LLVM that's part of the user code, it wouldn't contain all of the LLVM code base, right? For example, we never instantiate a GEP right now, or we never instantiate, a bunch of the user-defined types.
We have
So
time for one more
subset.
question.
Yep.
So is pnacl approach going to replace nacl? And what's the current statistics? It's clear that pnacl apps number is growing, but
Yeah. So on the browser side, native client is only enabled for the web store, right? So who knew? Chrome has a web store, and you can download applications that uses native client. Applications in the web store can also use portable native client if they want to, right? But native client is not going to be on the open web, right? You can't, we will not allow it to go to a web page and you load x86 code as is. So pnacl is built on top of native client, and it'll continue using native client for the foreseeable future. But as I said, we want to be able to experiment with the sandbox, right? So in certain cases, we'll use different types of sandboxing in the future, right? So in a way, it's trying to supersede native client, but it'll be a very slow process. And there's a bunch of other ways that native client is used outside of the Chrome Web Store. For example, if you use Quick Office on the Chromebooks, the kind of Office replacement, that uses portable native client, which happens to target native client, right? So there's a bunch of different uses or in servers or stuff like that that aren't likely to go away anytime soon, right? So we are trying to supersede native client, or more, rather we're making it an implementation detail of portable native client, right? So that if you wanted to have portable native client within, say, a different browser, it could be completely independent of native client, right? It wouldn't have to use any of the native client code base, right? And that's one of the things we actually want to showcase and experiment with to show that our portable format isn't just tuned to native client, right?
Okay, I'm afraid we're running out of time.
Can we keep going with questions? People can go to the coffee break if they want.
Oh.
Coffee break.
We should break, and people who want to ask a question should go down the front. That's general convention.
Thanks, JF.
All right, thanks.